All right.
So we're going to do the first part is just sort of picking up some other topics from chapter 13, and then the second part we'll do a lab.
I got a question.
Yes.
I was looking over the homework,
Yes.
and it has a formula that says area equals pi dimension squared over 4.
Oh.
4. Where'd they get the 4 from?
All right. So area of a circle is
Okay.
pi r squared,
Right.
and the radius is just half the diameter.
Okay.
So if we plug that in for the radius and get a better marker,
So that'd be,
pi times, so we get 1/2 times the diameter squared, which squares both things in there, so that's pi times 1/4 d squared, as we squared each of those.
okay.
That's where the quarter comes from.
That's what I wanted you to know.
Typically in math class, you get pi r squared, and then if you're given the diameter, you just cut it in half.
Okay. Because half of 2 radius equals a diameter.
Right. The general reasoning for why you would use this formula as opposed to that formula is that if you're given diameter, if you divide it in half, some students have a tendency to then round it. If you don't round it, it doesn't matter. If you do round, then you've lost some information. So it depends on how you want to approach it. But either one works. All right, so we spent yesterday talking about basically how a material reacts under a longitudinal force. And in that investigation, I guess we started out with just the simplicity of Hooke's law, and we'll get into the Hooke's law in more detail in chapter 14, I believe. Well, simple harmonic motion definitely exploits Hooke's law. So yesterday, material, if I pull it like that was our exploration. Now let's take a look at a material, and instead of pulling it, I'm going to push on it. So let's say that I have a fixed end down here, and I push at one end. Slinky works quite nicely for this. As I push on it, it deforms off to the side. And so how much it deforms is captured in what's known as the shear modulus. And the other symbols for shear modulus, of course, these all go by different names. There are 2 other symbols that I have seen in various bits of literature. Sometimes big G is used, and sometimes the Greek letter eta, E-T-A. Correct letter markers. Oh, wait, does this work? So that's the Greek letter eta. I'll be sticking with S, which is what your textbook uses. And so, as before, when we were looking at a ratio within, I guess, the elastic region, we had stress over strain, and so this becomes shear stress over shear strain. So I have some force there. I want to make sure I get the right area. Yeah. And it's still force divided by area here. That area, though, because I'm pushing from the side, it's not necessarily obvious which area I'm talking about, but the area I'm talking about is still the cross-sectional area up here. So the area of this part, or if I went so bold as to try to do a 3D diagram, or simulation of a 3D diagram. So I apply a force up here at this edge, and area of that top surface, where the bottom is fixed. But how do you measure strain? Because strain before was basically the change in the length over the initial length, but in this particular case, we're not really dealing with a change in length. What we are dealing though is with, as this thing pushes that way, it goes from, lack of coordination, it goes from upright to at an angle, and so that angle there is what we're now using for strain. And I will label that as phi. So as we push on it, so let's just do a side view. That is sort of the initial setup right there, and I'm going to dot it out because that's going to change. Well, those parts don't. And over exaggerate the influence. This angle right here is phi. So if this initial length is L, and that distance there is D, there's another form that the textbook offers using what's known as the small angle approximation, which we do see later on. So let's talk about the small angle approximation. How many of you have dealt with this before? I'll take that as none of you. So first off, we need a small angle, so we symbolize that as if we have some angle, theta, which is much less than 1. When you get the two less than symbols next to each other, that means much less than. And also notice that I have no units next to 1. So if I don't have a unit written there, and I'm talking about an angle, what unit is implied?
Degrees.
No, degrees you would have to actually write it.
Radians.
That's the other one, yes. Now why can I get away with not writing anything here when it's radians, but with its degrees I have to write degrees? What is a radian?
Two pi radians.
All right, so you got the translation between the two. So
circle radius is.
So in a circle, how many degrees?
You got 4 radians in a circle. You got a circle and you got diameter broken down in a radius.
You're hitting some keywords there, but it's more than 4 radians in a circle.
Well, go from the point in the middle circle to outside, that is a radian.
That's a radius.
A radius.
I'm talking about radians.
So you have more than 1 radian in a circle.
Right. Anybody know how many radians there are in a circle?
Yeah, like 360 something.
No, you have
It's
6
360 degrees.
Yeah, 6 radians.
It's closer to 6.
Well, radian is like 50-some degrees, so.
All right.
The
I
6
don't remember
radians.
exactly the number, but.
Let's
Yeah.
just drop back just a little bit here. Why are there 360 degrees in a circle? Where did they come up with that?
Well, it's
Because
kind
someone
of,
said so.
Who? Not looking for a person, looking for a group. What group started out with 360? You were about to say something, John.
I was about to say that degrees are arbitrary because you can have 8,000 degrees in a circle, it just depends on how many, rotations of the circle it is.
Ah, okay. It's arbitrary for, I would claim it's arbitrary for a different reason. It is man-made, I mean, somewhere along the line, there was a group that made it 360. You know, a little bit more sophisticated than because someone said so. Sort of. All right, so let's go back to the Babylonians. Didn't necessarily have to write it up there, and especially the way I wrote it, probably worthless. The number 60 was very special to them. They had at some point attached religious significance to the number. And it actually is a really convenient number because it is divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. It's divisible by 12 numbers there.
Right.
And so it's a very convenient number to work with, and so once you associate it with some significance, take it one step further. An equilateral triangle also had significance as one of those perfect shapes. And so why not bring the two together? And so they make that 60, 60, and 60. Now, if I got an equilateral triangle here and I want to sort of form a circle in a sense, well, the wrong way there, but we'll adapt. And then, if you play Trivial Pursuit, it's like the pie the piece that you're trying to fill up. So if each of these angles is 60, and I can take 6 of these equilateral triangles and fit them quite nicely together so that they form a complete shape, then I got 360 going all the way around. That's where 360 degrees comes from. Now, what point they slap the word degrees on there, I don't know. So I was attributed to the 19th century. There was a big push to try to get rid of all of the artificial aspects of mathematics. They wanted to get it down to things that were just natural. And so they realized if you take a circle, all circles have a radius. If I take that radius and I wrap it around the side here, that angle right there is the same regardless of the circle. If I take the radius of any circle, wrap the radius around the side, I get an angle, and that angle is always the same, and they said, let's let that angle be 1 radian. So then the question is, how many radiuses, or radii, can I wrap around? I guess 3 would be just slightly shy of there. So how many can I wrap around? Well, what's the circumference of a circle?
3.14.
Looking for the formula.
2 power.
2 power.
And that's how many radiuses you can fit around the rim of a circle, 2 pi. And so since there's 2 pi radiuses that will fit around the outside here, there must be 2 pi radians on the inside. And so 2 pi radians is the equivalent of 360 degrees. Likewise, pi radians is 180 degrees. Now, the unitless aspect of it is the relationship. If I have 1 radian as an angle, I've got an arc length that's 1 radius. 2 radians, 2 radii, and so forth. They're directly proportional. And so you can come up with a formula here that the arc length, not the same as that s, this is the lowercase s, the arc length is equal to r times theta, and where theta is in radians, And so therefore theta, just divide by r, is the arc length divided by the radius. And if the arc length and the radius are the same units, they would cancel out. We'd be left with nothing. So if you're talking about angles, if there's no unit written there, it is assumed to be radians. Typically, you would write radians in there if you're trying to communicate something more specific, as opposed to, if I write radians in there, then you know that I didn't, that it is radians. If I left it blank, there'd be the question of, did he mean to put degrees there, or is he talking about radians? You don't know whether I was being forgetful or just deliberately just didn't bother writing it. So a radian is a unitless unit. All right, so much less than.
So much less than 1 radian.
Yeah, so if the angle is much less than 1 radian, which was 50-something degrees.
57.29.
There we go. Then, the sine of the angle in radians is approximately equal to the tangent in radians, which is approximately equal to the angle itself. And you can try it out. So if theta is 0.1 radians, what is the sine of 0.1? What is the tangent of 0.1? And what, well, theta is 0.1. Someone be kind enough to do that?
Point 0.0017453284.
0.001?
7.
I would, is your calculator in degrees?
Uh-oh.
Sine of 0.1 degrees is a really tiny number.
Let me go back, put in radians.
0.1, basically.
It could-
0.0998 for sine.
0.0998.
Yes, for sine, and 1.1003 for tan.
0.1003.
3.
All right. So notice how they are really close to each other. Now, one of the reasons for this is pre-calculators or any sort of computing device, you needed to be able to do approximations that would save you time. And this is one of them. Now, if you're somewhere around 30-something degrees, you're 5% off between the sine of the angle and the angle. At 40, somewhere just shy of 45 degrees, you're 10% off. But typically, when you're doing much less than, typically it's less than 10% of this. So if theta is less than 0.1, small angle approximation is a legitimate technique. So if we look at that, so let's think about tangent, some right triangle trig. If I have a right triangle, sides A, B, and C, and that's my angle theta. Tangent of theta, cosine of theta, sine of theta. What's the tangent of theta?
Opposite or adjacent,
Which in this case would be
Cosine.
B over A.
cosine of theta.
It is an over hypotenuse A over C. And
B over C.
Yep. Cosine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. I'm assuming everyone, if you've forgotten, this should still look familiar to you.
Mm-hmm.
All right. So in our particular case here, if my angle phi here is small, I can use a small angle approximation, and then phi is approximately equal to the tangent, which would be d over L, the opposite over the adjacent. And so that's f over a over d over L. So if phi is small, which FL over dA, I think the textbook takes it that far. Yeah. And shear modulus also has another name, because you can't have too many names for the exact same thing. Modulus of rigidity. Any questions up to here? And the last thing I really want to discuss is the bulk modulus. As we dealt with, I pull on this thing, it will get longer and skinnier. We've now at least talked a little bit about, I push on it and it will tilt by how much it will, I guess, be displaced off to the side, is captured in this modulus of rigidity or shear modulus. We now, if I take an object and say I put it in the depths of the ocean, it's now being pushed on from all sides. What would you expect to happen?